everyone, welcome to this next episode of Explain Like I'm 5. Today we're going to talk about laws of exponents. As I was small in middle school, I always struggled with how these laws made sense. We are made to do a lot of problems using these laws. That's why we really know what these laws mean or how these laws function. But then we are never told what's beneath them or how do they come into the form that they are in. So that's what the major problem is. That's why today I'm going to start. That's why I'm going to start right from the scratch and tell you how these things make sense, if they make any sense at all. So firstly, before I start, I would like to talk about exponents, what exponents are, and then through a definition that you and me will be making in a few minutes now, we'll talk about how we can derive or understand what's happening behind these 6 laws or supposedly so-called laws. So when you talk about exponents, what are exponents? Basically, exponent is repeated multiplication. So if there is a number called 2 and I write something in its subscript. So what does this mean? The 3 is called exponent of 2, but then what is the real meaning? What is the real meaning of it? I mean, if there is 2 raised to the power of 3, or if 2 has an exponent of 3, what it basically means is that 2 has been multiplied 3 times. That's what we are told in school too. I think most of us can empathize with that fact. However, I'd like to tell you a little different way of thinking about this 3. So according to me, as I see it, this 3 is something that has appeared because we added something right down here. Don't you think so? If you don't think so, I think you'll be really thinking about it in a few minutes because I'm going to tell you how. So what we do is this is actually a representation of something, right? 2 to the power 3 is representation of something. And what is it representing? It is representing that 2 has been multiplied 3 times. But how do you go from here to there? So what do you do is you see what's being represented, what's being multiplied with itself, and how many times. To calculate that, you assign a value of 1 to each element. Like this 2 has a value of 1, for example. This another 2 has a value of 1 as well. And the third 2 has a value of 1 as well. And what you do is you take those values, you add those values, and what do you get? 1 plus 1 plus 1 will be equal to 3. And that's why the 3 is right down here. So in fact, exponentiation is, or exponent is, the sum of all those values that have been assigned to the thing that is multiplied repeatedly. That's what it is, if you want to put it in simple terms. For example, if there was another 2 right down there, if there were 4 2s, for example, I would have assigned the last 2 with a value of 1 as well, which would mean that 1 plus 1 plus 1 would be equal to, I add them all, and that would be equal to 4, right? So instead of this 3 right down here, I would have a value of 4. So if you see it this way, I think that you'll be really agreeing with me when I say that exponentiation is basically addition. But then in real addition, in true addition, what we do is when we add 2 plus 2 plus 2, what do we do is we add those 2 together. We add the coefficients together. So here this 2 is the base or coefficient while 4 is the exponent. So when we add 2 plus 2 plus 2, what do we do is we write 6 because we add them together. But then when you multiply 2, what do we do is we write the base as it is. We write the base as it is. This is just a notation. Don't think, where does this come from? Why do we write the same base? It is just a representation, right? So what we do is we write the 2 and at its superscript, what do we write is we add the assigned value. This has been assigned a value of 1. This has been assigned a value of 1 as well. So 1 plus 1 plus 1 will be equal to 3. So it's as simple as that. Now, if you look at it this way, what we're going to do in a few minutes is going to be really interesting and really easy as well. Because I'm going to talk about these six laws, which I think are really confusing if you stare at them for a while. Firstly, let me start with how x to the power 0 equals to 1. Now, when I saw this, it really amazed me at first. I thought that there was something really creepy going on inside it because no matter what value of x you put, you'll always get 1. No matter if you put 100 million or you put just 1, you're always going to get a value of 1. Now, why does that happen? I really thought that this was really weird. I never could garner the possibility of putting any value of x and getting a same result, and that too unit answer. that was really interesting for me. And in mid school, I really struggled with that as well. But now I know it. I think it is my responsibility to tell you why, or I think it really feels glad to tell you all how this happens, or what is happening beneath it. For this, I'm going to show you, firstly, I'm going to show you a little intuitive thing at the end of this video. However, I'll be telling you a rigorous proof of how these two things can be derived right from algebra. But then now, I think this will be really interesting to see how x to the power minus 1 will be equal to 1 by x, and x to the power 0 will be equal to 1. I think this will be really interesting to see using geometric series. If you don't know what geometric series are, don't be afraid about them. I'll be telling you about them in a while. So we know that 2 to the power 3 is equals to 8, because this means that 2 has been just been multiplied 3 times. So 2 into 2 into 2 is 8. 2 to the power 2 is 4. 2 to the power 1 is 2. We just know what's happening above this, right? We don't really know what 2 to the power 0 or 2 to the power minus 1 is for a moment. Now, what you can see is a pattern creeping out here. If there is 8, and if I go downwards, then I get 4, which is 8 divided by 2. If there is 4, and if I go downward, I get 2, which is 4 divided by 2. Notice how while I'm going from one term to another, I'm multiplying each term by 1 by 2, or dividing each term by 2. That's what a geometric series is. In a geometric series, the consecutive terms have a common ratio between them, so that when you multiply one number by the common ratio, you get the next number. So if you want to calculate what 2 to the power 0 is, what would be the natural course by looking at this pattern is to multiply the 2 by 2. That's how you get 1. So 2 to the power 0 will be equal to 1. If you want 2 to the power minus 1, then what do you get is 1 divided by 2, because that's what the natural course that's being followed here, 1 by 2. So now when I see this, it really answers the questions that I was asking earlier. Why would any value raised to the power 0 would be equal to 1? Because no matter what was here, for example, if there was 1500, then I would have divided 1500 by 1500, because in this whole series, the common ratio would be 1500, because I'm raising 1500 each time, because I'm multiplying by 1500 each time. So I should have divided by 1500 each time to return to the previous value. So if there were 1500 here, I would have gotten a value of 1 as well. So no matter what the coefficient or base is, I always get the same result to the form to something power 0. I'm going to get 1. So this really answers the questions that I was asking earlier. So I think you can empathize with me now when I say that x to the power 0 is equals to 1, and x to the power minus 1 is equals to 1 by x. Don't worry about this. I'll be telling how this can be derived afterwards as well. Now, the third law that I'm going to discuss today is going to be how x to the power a dot x to the power b is equals to x to the power a plus b. I know that most of you know already that this is true for any axis, for axis belonging to real number, and a and b is belonging to real number as well. But then why does, or where does this plus come from is a major question, is a really interesting question as well. But now, since I already told you how exponentiation is just repeated multiplication and adding the assigned value of each coefficient, I think it's going to be very difficult to see how, or where does this plus come from. I think it's really interesting now after we've defined exponent in such a way, right? So if there is x to the power 3 and it has been multiplied with x to the power 2, I already told you how x to the power 3 is x multiplied 3 times, and x to the power 2 is x multiplied 2 times. I think I can really go from this step to this step. But then if you look at the whole line now, there are 5 axes that have been multiplied each other. So I assign 1 to each of those coefficient and add them 1, 2, 3, 4, 5. So that is 5 now. So which is equal to 3 plus 2. So I think it's really simple that I say x to the power a dot x to the power b is equals to x to the power a plus b after I define exponent that way, and I see this example where x to the power 3 has been written as 3 axes multiplying with each other, and x to the power 2 means 2 axes being multiplied with each other, and all of those multiplying each other would be 5 axes multiplying with each other. So that's how addition creeps into exponentiation, and you should really have this sense of how addition is also important when you talk about repeated multiplication of the same number when representing it. So our representation is such that we assign it a certain value and add those values. The value is always going to be 1 because we assign it as though we are counting it. That's how it works. Now, after you've seen this tree number, I think it should be really easy and not really mundane to see how x to the power a divided by x to the power b is equals to x to the power a minus b, because x to the power 5 divided by x to the power 2 should be equal to, in the numerator, it should be x multiplied 5 times, which is x dot x dot x dot x dot x. At the denominator, x to the power 2 should be 2x's being multiplied with each other. Now, because x to the power x dot x is equals to x squared, and there's x squared down as well, when you divide them, they will yield a result of 1, which when multiplied can yield the same result. So it is not really necessary, because they can cancel each other out in simple terms. So what is left is x to the power 3, which is incidentally x to the power 5 minus 2. So it's just that we subtracted the number of x's that were down from the number of x's that were in the numerator. So this is all about numbers. This is all about counting. This is all about addition and subtraction. That's what exponentiation is. It's really as simple as that. Now, when you talk about fifth law that we are told, it's x to the power m raised to the power of n, and how that equals to x to the power mn. Now, what always amazed me is this formula, because this is really interesting. First time, because look at this. There is m and there is n, and it looks as if the bracket has been thrown off and this n goes and sticks with m. I thought it this way for a long period of time. This was how I always thought. Basically, this is how I always think now as well. Sometimes when I'm not in right brain, I remove this bracket and I think that n jumps and catches m, and then there is m dot n. That's how it works. They're glued together forever now. That's how I fantasize it. But then, what is the real thing happening here? It's not, of course, that the bracket has gone and n has stick to m. It's not just that. What is happening is the same thing. Like, what you need to understand is, once you recognize that exponentiation is repeated multiplication, and what you write at the top of that base is assigning values and adding those values, it really becomes really easy, right? So if x to the power 3 is raised to the power of 2, it means that x to the power 3 has been multiplied twice, which means that x to the power 3 dot x to the power 3. Now, since x to the power 3 means that x has been multiplied 3 times, it's x dot x dot x, and this also means that x has been multiplied 3 times, which means x dot x dot x. Now, x, if you look at the whole line, you'll see that x has been multiplied 6 times. So that's equal to x to the power 6, which incidentally is equal to x to the power 3 into 2. It is really interesting, isn't it? X to the power 3 into 2. So x to the power m whole raised to the power n should be equal to x to the power m multiplied by n. That's what it is. Now, in rule number 6, this is probably the last rule that we're going to talk today. We are told that this is a distributive property, but we just taught that technical jargon, but then we never said why this distribution rule works as well. I have this easy understanding of how this works. If there is xy raised to the power of 3, this means that xy has been multiplied thrice. So xy should be multiplied thrice. Now, since I can order the multiplicative terms each anyway, for example, if there is 2 times 3 times 5, then it is equal to 2 times 5 times 3, because changing the order of multiplication doesn't change the answer. Maybe we can do a next video on why this is true, but then again, let's focus now. Let's focus here now. So x can be brought together, y can be brought together as well. So x, because there are 3 x's that are being multiplied with each other, I think you should agree if I say that this is equal to x to the power 3, and times y has been multiplied 3 times, so that should be equal to y to the power 3 as well, right? So xy whole raised to the power 3 should be equal to x to the power 3 dot y to the power 3. It looks like this has been distributed, but then it gives a clear sense of why is this distributed, because everything is multiplied 3 times. So x is also multiplied 3 times, y is also multiplied 3 times. That's why x to the power 3 and y to the power 3 come here. It's not just that this 3 goes and flies and goes here as well and makes copies of itself by what, I don't know, asexual reproduction or what, and then goes here and then goes here as well. It's not how you think about it. Mathematics is not to be thought as if the numbers are doing asexual reproduction each time. That's not how you think about it, right? So these are the 6 rules that I promised I would tell you. I also promised you something, that I would give a rigorous proof. I don't know if that's what you call rigorous, but then a proof of these 2 these 2 laws, as they call it. So I think you should agree with me if I write x divided by x is equals to 1, but then each x has a power of 1, because as I already said, it is how many times it has been multiplied. So x is equal to x being multiplied one time only. So I think I think you can agree on me in that part. So x to the power 1 by x to the power 1, but then I already told you how x to the power a divided by x to the power b is equals to x to the power a minus b. So x to the power 1 divided by x to the power 1 should be equal to x to the power 1 minus 1. That's equal to 1 as well. Now 1 minus 1 is 0, so x to the power 0 is equals to 1. I think that this completes the proof. That's how you think about it. For x to the power minus 1 is equals to 1 by x, I will continue upon the result that I just got. X to the power 0 is equals to 1, and 0 is equals to 1 minus 1. I think that's clear as well. Then what's happening in this state? Then see, if I know that x to the power a dot x to the power b is equals to x to the power a plus b. If I can go in the forward direction, why cannot I go in the opposite direction is the question. If I can write x to the power a dot x to the power b is equals to x to the power a plus b, but then I can also write x to the power a dot x to the power b when I see x to the power a plus b. So since this is x to the power 1 plus minus 1 is equals to 1, I can also write x to the power 1 dot x to the power minus 1, and that should be equal to 1 as well. If you divide both sides by x, then what do you get is, if you divide both sides by x, then what do you get is, you cancel these x's together, which will mean that x to the power minus 1 will be equal to 1 by x, and that's how you get the proof of x to the power minus 1 is equals to 1 by x as well. So that's how we complete the chapter, or it's not actually a chapter. This is how we complete how laws of exponents can be intuitively seen, or seen when seen easily, and we try to peek into what's going beneath these 6 formulas. I think you really enjoyed it. I really enjoyed making this video. Thank you so much. We'll be back with another video on a different topic. We'll be always trying to explain like we explain to a 5-year-old. Thank you so much for being wonderful audience. We'll see you again. Keep watching, keep following us. Thank you so much.